Okay, next I will continue. I'm Vikas Rathore. Yeah, graph isomorphism problem is a classical problem with unknown complexity status. The problem asks whether to given the graph G and H are isomorphic. That means the action between the vertices of the graphs. That the edges to edges and non-edges to non-edges. There is a bijections between the edges to edges. Here in these papers there are many times you can see the big O notation. So I will discuss the big O notation. Something big O notation is used to measure how the running time or a space requirements of your programs grows as input size grows. Means the how much time taken by programs like the polynomials, it will be depends on our input size. Take the 1 degree of the polynomials n equals to v. Here we will neglect the constant terms b, because the big O notation refers for the large values of n. So for key fastest growing terms, we will take the a into n, and I will use big O notation of the n. Similarly, we can see in a second degree of the polynomials, here will be use only the big O notation of the n squares. Some persons take the big O notation of n square plus n. I am not taking here because it will be the irrelevant. Since the for the large value of n, the values of n will be the much smaller than the n square. Here you can see the n upon 2 blocks, n upon 2 square blocks, and after the k iterations it will be the n upon 2 to the power k blocks. So n equals to 2 to the power k, taking both sides log n equals to k log 2, and which implies that the k equals to big O notation of the log n. So here we discuss the history and the main results. Graph isomorphism problems for the graphs with n vertices. So here the one of the first results was given by the Philote Millers in 1980, and he gave the time n ki power big O notation of g, where the g is the Euler genus C. After 2 years, Lukes gives the another way to define the times, that n ki power big O notation of the d, where the d is the maximum degree. And after 1 years, the Wise with the Lukes could extend the another results, and he gave the another way to keep our big O notation of the under root n log n. Here Bawai calls the moderatory exponential times, that's still an exponential time bound, but the exponent grows much slower than the linear functions. Bawai calls this time is a moderatory exponential time. After some times, in 1990, uh, for the graph of the tree with the tree with t, time will be the n ki power big O notation of the t. And in 1991, the Ponomorco gave the another way, n ki power big O notation of h. Handworks numbers h. Now the graph isomorphism, the most recent bounds. Trivial bounds factorial n, exponentials big O notation of n under root n's, Bawai is called the moderatory exponentials. In this paper we will discuss and we will take the exponential of n log n in case of the quasi-polynomials. So here, before we discussing the graph isomorphism quasi-polynomial times, for which first of all we are going to a permutations groups, then we will see that how we can relate the permutations groups to the graph isomorphism. So here the let G equals to the symmetric group of A be a permutations groups with the n number of the elements. A stabilizer of x belongs to A. Gx equals to the P belongs to G at x power P equals to x. So now this is the results. This is the central groups theorem results, which is the heart of the entire algorithms. That is called the unaffected stabilizer's lemma. Let U be the set of unaffected elements of A, and G be the point-wise stabilizers of U. That is the G equals to the intersection of the Gx. Here we talk about the point-wise stabilizers of the set. Here I will take the very small values of m. M is greater than or equals to the maximum of 8 comma 2 plus log n. This is not a fixed that 8. So then T of G equals to the alternative group. Yeah, you can see from the graph there is a mapping from G to AM. Here there are the some stabilizers like a Gx, Gy, Gy, and the intersection of these stabilizers is the Gu, which is mapped to AM. Yeah. Now the question is how we can relate the graph uh, permutations group to the graph isomorphisms. Since the Bavai have been working for a string isomorphisms, Bavai quasi-polynomials graph isomorphisms are very complicated. So let us describe an algorithms to do the we have to know about the any group calculations can be done in polynomial time. If we an input as the two graphs G1 and G2, then what we can do? We can do is actually transform the graph into a equivalent strings. Bavai algorithm is actually for a string isomorphisms. Graph isomorphism is just a special case of the string isomorphisms. And stated that the similar to the graph isomorphism problem, except we are looking for a leveling over the alphabet rather than a vertex set. Okay, so now first of all I like to define the more general problems. That problem is what I am going to the address of this string isomorphisms problem. We have a strings, we have a permutations, then we can apply the permutations to these strings and then we will get the another permutations. X tends to x power p. Apply the permutations to the strings and we will get the another strings. Now the in 2015 Vavai breaks the resolves and he showed the graph isomorphism problems for the graphs in journals can actually be decided the quasi-polynomial times. That's an exponential functions. And he give the results that the graph isomorphism problems for the graphs with n vertices can be decided in a time n ki power b connotation of the log n ki power c for some constant c belongs to natural number. Here the questions arises that the for which parameters of k graph isomorphism problems be decided in times n ki power b connotation of the log n ki power c. So such a running time bound clearly the quasi-polynomial time bound as a usual parameters as treat as the of the graph or maybe a maximum degree of the graph or a Zenes graphs are usually bounded by the number of vertices. On the other hand, such a running time bound also be generalized the results. Actually in 2018 Groh and Newman Sedgwick gives the answers. It is the partial answers and he give the results in the sense of the maximum degree t n ki power Vigo notation of the log d power c. In 2020 another results in the sense of the Euler's genus n ki power Vigo notation of the log g power c. And in 2020 in case of the tree with t n ki power Vigo notation of the log t power c. So here by figure you can see that it is the graph classes. Here the genus of the graphs describe the minimum Euler characteristics on the surface in which you can embed the graph, and the maximum degree describes the maximum number of the neighbors of the given vertex in the graph. Tree width of the graph describe how tree like the graph looks. So here Balabi stops, and I will give the some overall idea about this paper. Actually, we can see the isomorphisms of the graphs by the simple way that we can see the same vertex, same edges, odd number of cycles, same, by which we can see the isomorphisms. But when you have a more number of the vertices, more number of edges, in case of the complicated graph, then what we do? Baba is working on a string isomorphisms. He and string isomorphism gives the ideas of the labeling of the graphs, taking a 1 and 0, by which you can easily see the isomorphisms between the graph, that the graph is isomorphisms or not. That's it for now. Thank you.